of integration by parts. And you can watch the first one if you wanted to, if you haven't yet. The point is that I want to show some of the different situations that happen. Ultimately, part 3 is going to lead to the trickiest trick for integration by parts. I think it's pretty nifty, and it will help make some of these problems a lot easier. Certainly, it adds a structure that makes a lot of sense after you practice it a couple of times by hand, doing the whole long form. Part 3 is going to have a short form way to get to that one. What I want to do is I want to show you why we might like part 3's answer. We got to go through some, math muck in order to get to it. Integration by parts, remembering that lipit, logs, inverse trig, polynomials, exponentials, and then actual trig functions. That's probably your best, although there are others that are out there. I really prefer this one. This is probably one of the best ways to identify your u function in the problem. In order to start this problem, knowing that we have no logarithms, no inverse trig functions, but we do have a polynomial. We have t, as in the t squared is the polynomial. And then that means that exponentials, which would happen afterward, this is going to be the, well, all of this is going to be the dv. Because we have to identify which of these parts are being multiplied together, which of them actually stack up into this formula. How do we line them up? So some work on the side is going to be that we need to identify u, which is t squared, and then we need to identify du, the differential of u. Yeah, it's a derivative, or derivatives and differentials are interconnected as terminology, as processes in calculus. But by writing it as a differential instead of derivative, it's going to give us an extra little bit of power here. 2t dt, the differential of t. The reason being is we should take this du equation and solve for dt. dt equals 2 over t du. And we're going to put that into the problem. Next, let me see here. Check that. Check that. There's something I need to make an adjustment on. I'm a little nervous about what's going on here, but I think we'll be okay. Yeah, we'll be okay. Okay. So then dv will equal e to the 2t dt. And I chose this problem to present to you because I want to remind you and drive home the point that as we integrate both sides of this relationship, we're going to have to use another u substitution process along the way. Or maybe you know a shortcut. If you're thinking about things, really intelligently, you know that in this nested or chain rule, we have to use some sort of u substitution in order to break it apart. And there's a common theme that happens specifically for this function. But let's work it through anyway. Okay, so I'm going to give myself some space for the v function, and I'm going to go back up here, and I don't really want to use u equals as my u substitution, so let's use star, right? Let's use star. And I'm trying also to avoid letters just for the sake of showing that letters are meaningless. I'm going to say that this 2t is the star. Then that means that the differential of star must be 2 dt. So if I solve for dt, divided by 2, I can replace this dt with d star over 2. I can replace 2t with star, and so the problem actually becomes the integral of e to the star times d star over 2, or really the over 2 is 1/2. So I'm going to push that all the way through the problem. Push it all the way through, all the way to out front. So I have 1 over 2 e to the star. And if you remember, I mean, just because we used x commonly, all of that, these symbols are just space holders waiting for further function definition. So e to the star, the integral of e to the star is e to the star. 1/2 e to the star. I don't need to write the integral sign anymore because I evaluated it. We shouldn't stick around with star. It is a problem that involves a function of t. So we're going to say this is 1/2 e to the 2t. Technically, there is a plus c out front, but that's not the final answer. And there's no need for us to be concerned with like maybe a multiplying or some other process is going to happen to the constants. So we're just going to leave that alone. We have the v equals 1/2 e to the 2t now. And that's kind of what I'm alluding to with that trick. Maybe you see a trick developing. Putting all of that together and using our uv minus integral v du, putting all of that in place, we're going to rewrite what we have as equals t squared times 1/2 e to the 2t. Perfect. Minus. Now we have the integral of v du. Now I'm experiencing a problem, a little bit of disequilibrium. Something about this isn't quite sitting right in my mind. Yeah, I want to keep going. I think there's an issue that I'm having with, oh, this is du. Yeah, what am I thinking? This is du. Oh, yeah, so I don't need that at all. I needed this for the ability to substitute, but no. Okay, so we're fine. So I'm going to go ahead and just ignore what I wrote there. Maybe it was useful, maybe it's not. Du and v, so it's v and then this expression. Yeah, that's what my disequilibrium. I was thinking that I had this 1/t situation I had to solve, and I'm like, that's never happened. Okay, so v function is 1/2 e to the 2t. I'm sorry, I keep moving the paper in and out. I'll leave it steady for a minute. Of course, this being a YouTube video, you are able to pause the video and, rewind it. Times du. So du is 2t du, and then, no, what am I doing here? Du, it's 2t dt. There we go, that's what I'm doing here. I need that parenthesis at the end. There, okay. All right, so the idea behind it is we've now taken our integral, and in the process of our integral, rewrote it. And this, let's focus on this integral. Can we do something with this? So to do something with it, we still have, maybe rewrite this a little more nicely. T squared over 2 e to the 2t. That's pretty nice, pretty concise. Over here on this side, the 2's and the 1/2's will cancel, leaving us with e to the 2t times t dt. Now, this isn't straight away a problem that we can just jump into. We're going to have to then do another anti-differentiation by parts, integration by parts, I mean. So that means we have to go back and using Lipit, figure out, based on these two functions, which one will we be replacing? Are we replacing the L, the I, the P, the E, or the T? Are we replacing the E to the 2t? Or are we replacing the T? Which one becomes our U function and then sets the stage for the rest of the problem that we do? Work on this side again. Here goes. So because t is technically a polynomial, we're going to make u be the t function. And then we're going to make du equal the derivative or differential of t. Therefore, it's dt. That's a good thing, though, because we only have just dt. There's no other function multiplying dt at this step. There was right here, there was the t function multiplying dt. That should be an indication to you, not that you're wrong or on the wrong track, but that you are not done, okay? So, meaning like we'll have more by parts processes to go through. dv must be everything else. So that would be e to the 2t dt. This is actually pretty good with these types of questions. We don't need to show all of what we did here with star, d star, etc. We just know if e to the 2t is our function, using our previous learnings, we can say that v is 1/2 e to the 2t. I wonder if that actually lets us, right? I wonder if that actually lets us figure out a way of writing any e to the power, right? We should see a relationship here. Moving forward, so uv minus the integral of v du. And because it's already negative, that's the key thing here, guys. Because it's already negative, all of this calculation has to happen inside the bubble of the integral, the second integration by parts formula. So uv v du, I'm going to write it out here, bring it over here in a second. We have the original. We don't have to mess with this, but it does need to stick around. This is trying to stick around from the whole problem. Then we have the parentheses, because everything that's going to happen in parentheses is meant to be the answer or the result of integrating that other integral, which requires another integration by parts. So in this problem, v would be t times 1/2 times e to the 2t. I can write a t that doesn't look ridiculous, or very, very annoying. Okay, minus the integral of v du. So du is dt directly, and we want that to happen. So in this problem, we would have 1/2. I'm going to move the 1/2 to the front. I mean, I want to write it twice. I'm going to acknowledge that this constant, we're just going to bring it into the front of the entire problem, e to the 2t dt, because dt at the end. And that is further inside or contained within the antiderivative, like that bubble, trying to solve it. So we have to keep going, right? In other words, there's still more to do. So in the still more to do problem, this is still going to be here. And we've already answered this question, so I don't really need to do much more u substitutions. We've already answered what it looks like when we try to figure out the derivative, antiderivative of e to the 2t. So this is t squared over 2 e to the 2t minus, allow me to do that in this moment. I'm going to do like several steps in this moment. T over 2 e to the 2t. Now I'm going to use the negative and say it's going to be plus 1/2. And then the derivative, no, the antiderivative of e to the 2t, like we've been seeing it, is 1/2 e to the 2t plus, well, yeah, I'll put the plus c in this moment because we are now fully moved past all of our antiderivatives. The plus c's have been shifted all the way out to the end, all of them every time an antiderivative happened. So therefore, now when we have no more integral symbols, we can say we have a plus c. There it is. The maybe simplify it out, right? So, but this is it right here. So we have equals, I'm going to save myself a step. I'm going to factor. All of these things have an over 2 factor. E to the 2t over 2 times t squared minus t plus 1/2 plus c. That's fairly concise. Thanks for watching this video. Stick around for part 3. Part 3, I'm going to show you hopefully what I can do with this problem and accomplish the same thing either in half the time or half of the paperwork. Thanks for watching. Bye.